morning. Welcome to new lecture. In this lecture I will review what we had before and I will solve some problem, real life problem, to see how we can approach to solve problems in mechanics of material. As you remember, we defined stress is a force per unit area. So normal stress is force per unit area and strain is equal to elongation per unit length. Normal stress always we will show with lowercase sigma, and strain, axial strain, we will show with epsilon, and it is equal to deformation over initial length. Let's again, I draw our example. Assume we have one rod. We apply tension force in centroid of the section. The initial length, for example, L0, and initial cross-sectional area, it is A0. In that case, stress will be force divided by initial cross-sectional area, and strain will be deformation divided by initial length. If we draw stress strain curve for linear elastic material, it will be one line, diagonal line. The slope of this line, tangent alpha, we will show with E. We call it Young's modulus. Young modulus is property, is a mechanical property of the material, and it measures the stiffness of solid. For linear elastic material, linear means stress and strain, they are proportional, and elastic means if we remove external load, we will not have permanent deformation. If we apply the load, we will have deformation. For example, in this example, we have deformation like delta. And if we remove this P, delta will vanish and we will not have any permanent deformation like rubber band, like one spring. So for linear elastic material, if you remember, I said Hooke's law is valid. Hooke's law in material is sigma, stress is equal E Young modulus times epsilon, strain. From here, because sigma is equal to P over A naught, is equal to E times epsilon is delta over F. So from here, delta deformation will be P L over E A. Of course, I can add here L naught and A naught means initial length and initial cross-sectional area. The reason I emphasize on the initial length and initial cross-sectional area, later on I will explain more, because we have two types of stress and strain. One we are using in engineering, we call it engineering stress strain. In that formula, always this is initial cross-sectional area, this is initial length. Another one, it is true stress strain, which we will use in the science physics usually. There we will divide it by area and length. I will explain later on why and what is the difference. For now, you should know this is initial cross-sectional area and this is initial length. I give you example for Young modulus. For different material, this will give you sense. For example, if I write the material name here, material, and here it is in SI unit, E Young modulus in SI unit, in the gigapascal. For example, for diamond, E is 1000 gigapascal. For steel, of course, depend on the type of steel, but roughly it is 200 gigapascal. For wood, it is almost, of course, again we have different type of the wood, but roughly it is 12 gigapascal. For plastic, it is around 2 gigapascal, and for rubber, young masses, it is 0.002 gigapascal. You see diamond stiffness is much higher if we compare diamond with steel or wood, and it makes sense. The way we will measure it, I will explain later in another lecture. I will explain how we will conduct tensile test, how we will end up with the stress strain curve, and what is the different point and location in this curve name, and what we will call different region. They have different names, and I will explain those in details later on. Anyway, this what we had before. Let's now solve example to see up to now with this formula can we solve any real life problem and how we should approach to those problems. Assume the first problem. Assume we have one rigid beam. Rigid beam means cross-sectional area is big and we neglect the deformation of this beam. This is rigid beam, and we attach here one hinge support. Here, this end, we have one rod. We attach this rod to the ground. Here, for example, to the roof or ceiling, and we have another rod here. This rod you see, two end, it is hinge, it means we call it truss member. If we have straight bar, two end is hinge, and we don't have any external load on this rod, we will call it truss member. In truss member, usually for in-plane 2D structural member, we have three internal forces. We have axial force, we have shear force, and we have bending moment. In truss member, we will have only one internal force. So usually in all structural member, if they are 2D structural member, in plane structural member, we have three internal forces. One of them is shear force, another it is axial force, another is bending moment. But if it is truss member, we have only one internal force, and we will call it axial force. So the material property for this rod, it is E, and the cross-sectional area, it is A. Pay attention, this E and A, they are known value. For example, it is from steel. We know E and we know the cross-sectional area. The length for this rod, it is 2L. The length for another rod here, assume it is L. This space, it is 2A, and this space it is A, and this space it is 2A. So let's I put name here point A, point B, point C. From A to B, the length is A, lowercase a. This lowercase a, again, it is known value, for example 2 feet. From B to C, it is 2A's. It means it is 2 times of AB segment. And here, Young modulus, again, it is E, and the cross-sectional area, it is 2A. So, both material for this rod, it is the same. For example, both they are steel, and the cross-sectional area, here is A, here is 2A. So, the cross-sectional area for this member is 2 times of this member. So, and this beam is rigid. So, we assume there is no deformation for this beam. We apply one load here. the load here is point load or concentrated load. The magnitude of the load, it is P, and you see the direction. Load value, again the magnitude of the load, it is known. So everything in this problem is known. We know the L, the magnitude of the L, it is number, it is for example 4 feet or something like that. This lowercase a, again it is length, we know that. This capital A is cross-sectional area, we know it. E, Young modulus, we know it. P, again is external load, I apply this P, I pull out this point C, so I pull down point C, and I know the magnitude of the P. Everything here is known, you can put number. I want to find delta C. I want to find delta C. If we have this type of structure, you can build this type of structure. It is simple. For example, instead of this beam, you can use one pen, or instead of these bars, you can use straw or something like that. Pin it and apply load to see what will happen. If we have this type of structure, if I apply point load P at point C, this structure will deform, and this rigid beam will remain a straight line, but it will rotate respect to point B, so it will deform something like this. Let's I draw more precisely. So it will deform something like this. So initially the beam is horizontal, point A, point B, point C. Then it will rotate like this. Point A will transfer to here, point A prime, and point C will transfer here, point C prime. Point B will be stayed in this initial location because we attach to the support. This deformation is delta C. It comes down. This deformation is delta A. It goes up. I want to find delta C. What is the delta C? How much deformation, how much deflection we will have at point C. We can solve this problem from two methods. Let's say we'll solve from two methods, and then I will compare. You are free to solve from any method you like in the exam, in the homework. So, from geometry here, we know this is initial position of the beam, it is horizontal. Then after deformation, it will be like this dashed line. Now we have to triangle. From geometry, we know from here to here it is A, and from here to here it is 2A. From geometry, I can write delta A over delta C is equal to A divided by 2A. So in these two triangles, delta A over delta C is equal to A divided by 2A. From here, what I have, I can write delta A over delta C is equal to 1 over 2. From here, delta C will be equal to times of delta A. This is one equation I found from deformation. I can write another equation using equilibrium equation. If I write summation of moment respect to point B is equal to 0, what I will have? For example, internal force in this member I show with Fc. Internal force in this member I show with Fa. So Fc will be here, Fa will be here. The reason I show this FC upward and FA downward because this member tries to return point C to the initial location, and this FA will try to return point A to the initial position. So they should be in this direction. Again, there is no difference. If initially you assume in the wrong direction, nothing will change. Only you will end up with negative answer, and negative answer means your initial assumption is wrong and you should change the direction. Anyway, so from here I can write, if I take moment respect to B, FC times 2A, FC times 2A minus P times 2A plus FA times A is equal to 0. FC times 2A, it is counterclockwise positive. FA times A, it is positive. External load P times 2A clockwise negative. I can write this equation using equilibrium equation. So from here I can write 2FC plus FA is equal to 2P. What I did here, I cancel A and then I took 2P to other side, to the right side, so it will become positive. Now I have these two equations. We know the formation in one member is equal axial force in that member times the length of that member divided by EA of that member. So how much is the delta C? Delta C will be internal force in that member, which is FC, times the length of that member, which is 2L, divided by EA of that section, EA. This is delta C. How much is the delta A? Delta A is equal to internal forces in this member, which is FA, times the length of that member, here it is L, divided by Young modulus times cross-sectional area will be, because E times 2A will be 2EA. So I have the delta C in terms of the force, I have delta A in terms of the force. If I substitute here, I will have FC2L over EA is equal to 2 times delta A. Instead of delta A, I will plug from here. I will have FA times L over 2EA. From here, you see this L from both sides, they will cancel each other. EA and EA, they will cancel each other. This 2 and this 2, they will cancel each other. And we will have FA is equal to FC. So from here I can write FA is equal to 2FC. If I plug this here in this equation, 2FC plus FA, instead of FA, I will plug 2FC. So in this equation I will have for FC is equal to P. From here I can write FC is equal to P over 2. So now I know internal force FC in terms of external load P. FC will be equal to half of external load P over 2. So because the external load, it is known value, now I know the magnitude of the FC. Now delta C is equal to internal force in this member, which is FC, here it is equal P over 2, times the length of this member, it is 2L, divided by E, A for this member, from here will be PL over EA. So We have external load magnitude because we apply that external load. So P is known value. We know the length of this member. We know 2L, so we can calculate half of that. We know L. We know the Young modulus because we know the material for this member is known. And we know the cross-sectional area for that member, so we can find delta C. We can find how much this point C will move down. This is one way to solve it. The method I use it, first I find the internal forces. I find the forces. Because first I find the internal forces which they were unknown. Initially they were unknown, but I find it in terms of external load. External load, it was known, but internal forces, they were unknown. Because first I find internal forces and then I calculate the deformation. This method of solution, we call it force method. So this method, we call it force method. First I find internal forces, then I found the deformation in terms of those. This is force method. So I find delta C. Delta C is equal to here PL over EA. I solve this problem one more time using another method, which we will call it stiffness method. See what is the stiffness method. The problem statement is the same. Everything is the same. I will remove everything here because I need space. Okay. Again, the same problem. Everything is the same. We have this structure. I want to find delta C. How I can find delta C? Initially, this rigid beam is horizontal. Then it will rotate respect to point B and it will rotate like this. Here we have delta C, here we have delta A. This member, I call it member 1. This member, I call it member 2. What is the stiffness, axial stiffness for member 1? Axial stiffness for member 1, axial stiffness always is Young modulus times cross-sectional area divided by length. So the axial stiffness for that member, it is E Young modulus times A cross-sectional area divided by 2L. This is EA over 2L is axial stiffness for member 1. Axial stiffness for member 2 is equal to Young modulus for this member times cross-sectional area divided by length again. So it will be EA here because our A is 2A. So times 2A will be 2EA, 2EA divided by L. So look at here, EA over 2L, this is 2EA over L. K2 is 4 times of KA1. I call this K. So this will be 4K. Okay. So stiffness here, if I substitute instead of this member, one spring. What is the stiffness for this spring? It is K. What is the deformation for this spring? Deformation for this spring is delta C. I assume delta C is equal to the delta. So the deformation here is delta, the stiffness for this member, it is K. How about this member, if substitute instead of that member one spring? The stiffness of that member is 4K. I calculated here, you see it is 4K. If this point C comes to the C prime, delta C and delta A, what is the relationship? Delta A over delta C, delta A over delta C from geometry, we know this is A, this is 2A. So delta A over delta C is equal to A divided by 2A. Delta C over delta A divided by delta C is equal to A divided by 2A. So from here, again, delta C will be equal to delta A. If I substitute instead of delta C, delta A in that case will be equal to delta over 2. So if point C comes to the C prime, the deformation here, the deflection is delta. Here is half of that, it is delta over 2. So here it is delta over 2. I refresh your memory. If we have one spring, I apply force to this spring and deformation is delta, we can write force is equal to stiffness of spring times deformation. Am I right or not? So, force in one spring is equal to stiffness of that spring times deformation. So here, what is the force in this member? Stiffness times deformation. So, Fc will be K delta. What is the internal force in this spring? Stiffness times deformation. Stiffness is 4K. Deformation is delta over 2. That is equal to Fa. So if I draw one free body diagram again here, pay attention, I'm doing here. Here the force Fa force will be 4K stiffness times deformation delta over 2 will be 2K delta. 2K delta. Here is support B. Force here, it is stiffness times deformation, which is K delta, and we have external force delta. If I write summation of moment respect to point B equal to 0, what I have? I have this force which is Fc. Fc is K delta times from here to here, which is 2A, plus force here, Fa, which is 2K delta, times the distance from here to here, it is A, so it will be 2K delta times A, minus external load times the distance from here to here, which is P times again 2A is equal to 0. From here, what we have? This is 2K delta A. 2K delta A, it will be 4K delta A equal to 2PA. A and A, they will cancel each other. This 2 will cancel from this 4 and we will have 2 here. So K delta will be equal to P over 2. So K delta will be equal to P over 2. I remove part of here. So finally we find K delta is equal to P over 2. What was the K? K was EA over 4 over 2L. K is equal EA over 2L. So instead of K, I will plug E A over 2L times delta is equal to P over 2. 2 and 2, they will cancel each other. From here, delta will be equal to PL over EA. Because this delta is equal to delta C, so delta C, deformation at point C, will be equal to P, external load, times L, times the length of this member, divided by EA. We get exactly the same answer. Here, what I did, I worked with stiffness of these members. This method of the solution, we call it stiffness method. So the first way I solve the problem, we will call it force method. The second way I solve the problem, we call it stiffness method. Depends on the problem nature. In some problem, it is easier to solve, it is easier and faster to solve that problem from force method. But in another type of the problem, it will be much faster if you use stiffness method. So my recommendation to you, practice, learn both methods very well. Depend on the nature of the problem. After practice, after solving hundreds of the problem, you will be expert. You will recognize immediately which method you can use and which method, if you use, you will end up with final answer faster. So please try to learn both methods, and if you learn both methods, in future you will see I am right. Some problem, force method, immediately you will recognize this problem, it is better I solve using force method. Or another type of the problem, you will figure out it is easier to solve using stiffness method. Thank you so much for watching this lecture. See you next session. Bye bye.